Hello everyone, I am Imonde. So in this talk, I am going to present our demo paper titled the demo version of RhythmEdge, which stands for Enabling Contactless Heart Rate Estimation on the Edge. This work has been collaborated with Zahid Hassan, Srini, Dr. Roy, and Dr. Mishra, and also this research work is supported by NSF Career Grant and US Army Grant. So let's get started. So the objective of this paper is to prototype a low computational, ubiquitous, reliable and stable remote photoplethysmography system for monitoring heart rate continually using off-the-shelf video cameras. Particularly, we aim to provide implementation details of developing remote RPPG systems in edge devices, which can perform benchmarking by measuring system parameters. So here, normally we have three different sections. First, we have included efficient deep learning based RTVG inference model, where we have implemented suitable model compression techniques. Secondly, we have executed our RTVG system on commodity embedded edge devices. And at last, we have tested our system under varying light conditions and different facial distances, and through which we have measured the stable performance under various device specifications. So the major contributions we are claiming in this work are: we provide the implementation details of our RTVG system. Secondly, the RhythmEdge is implemented by elaborating the key details of our system architecture and a benchmarking approach. And also, uh, to expedite the research in this field, we have open source the software stack and instruction to reproduce the RhythmEdge work. Now, I'll discuss briefly about the RhythmEdge architecture here. RhythmEdge work is developed in three sequential phases to extract PPG from camera sensor captured from facial video data. The phases are input sensing, PPG inference, and output PPG processing. The first phase requires video camera sensors, and the later two components entirely take place inside the edge device. So in the sensing phase, the limited resource edge devices receive the input facial video to infer PPG form. Our RhythmEdge can operate in real-time mode and also in offline mode. So in real-time mode, the edge devices senses the input video via wired connection, which is USB-C camera, to capture video on the fly. Alternatively, in the offline mode, the edge devices receives memory chips or cloud platform like Drive, GitHub to receive the captured facial videos. The real-time mode and offline mode vary only in the sensing phase. Now, after receiving the video, the edge devices infer RPVG in two steps. Firstly, it performs video pre-processing using OpenCV library. The OpenCV crops and resizes each of the frames of the input video. Further processing prepares input for the RPVG model to infer by accumulating 40 consecutive frames. In practice, the batch of 16 samples or equivalent video of 22 seconds at 30 fps altogether for the model to infer. The edge device also uses the installed version of TF-Lite runtime implementation to infer the PPG form, the proposed video. Here, it uses the compressed TF-Lite model to extract PPG. Finally, it returns the concatenated PPG output for the 22 seconds of corresponding video. Now, at the last stage, the edge devices infer heart rate by performing frequency domain analysis of the inferred PPG signal using the first Fourier transform. The edge devices send the predicted heart rate with the timestamp to the user email via send mail communication protocol. It also stores the longitudinal HR information of the user's convenience. Now, some brief description about the hardware requirements of our hardware and software requirements of our RhythmEdge system. Our RhythmEdge system is compatible with three of the popular edge devices like Jetson Nano, Google Coral Board, and Raspberry Pi. It can be developed using one of these three devices. We have also tested our system with different camera sensors like DSLR action camera and USB-C HD webcams. To run the RhythmEdge application, we require the software stacks of TensorFlow Lite, OpenCV, FFmpeg, SendMail, Python 3, and HDoc. We provide further details in our project GitHub page that you can find in the main track paper. Now, some details on the system monitoring. We monitor and benchmark RhythmEdge system to study the robustness and feasibility of it. Particularly, we monitor the memory utilization, time complexity, and power consumption in RhythmEdge components like OpenCV video preprocessing, data loading, model load, inference during their executions. We have used JTOF for Jetson Nano and HTOF for other two devices for memory profiling, time library built in Python for system lag measurement, and an external device for power consumption measurement. The detailed results are provided in our main paper. Here you can see a demo version of our work where you can see our RhythmEdge is working. First, subject is placed within 3 feet of the webcam, and upon running the bash script, you can see the video is being automatically captured, and 22 seconds of data are being used for EVG inference. And through the SendMail protocol, the captured RPVG value and all the relevant data are being sent to user's email ID. And also you can continuously monitor memory power and time complexity of the system through the connected devices. So in conclusion, we provide a detailed instruction and component description to develop RPVG system in the edge devices in this work. We also open source the instructions and software stack to reproduce the works. We demonstrate our system on 3 devices with heterogeneous edge architectures. We perform feasibility studies to ensure system operation. We also validate and test our system under various realistic conditions. Thank you. Any kind of questions are welcome. Thanks.